Okay guys, I decided to make a video lesson to help you guys out so you can pause, you can re-watch, you can watch it 20 times hopefully to get this stuff down, because I know it's weird and hard to understand. It's late, need to get out of here, so I'm going to get this done in one take. It's probably not going to be that good, but hopefully it helps. Okay, so we spent a lot of time looking at the periodic table. Periodic table has all the elements of the universe, okay? Everything that you can touch that is matter, it's composed of these elements, all right? Every element has a unique atomic structure, okay? This is a Bohr model, okay? It's our best way for modeling the atomic structure, okay? We can draw it in 2 dimensions on paper. It tells us how many electron orbitals there are and how many electrons are in each one of those orbitals. Okay, very useful, simple to draw. You can draw it simply by looking at where, you can draw the Bohr model for each element simply by looking where that element sits on the periodic table. Okay, before we get into that though, let's talk about the atomic structure again. Okay, remember the atomic structure is a nucleus. Okay, this is the nucleus. Okay, I told you this wasn't going to be good. Nucleus. Okay, so I can't remember how to spell nucleus. Okay, so the nucleus is composed of what, guys? Yes, protons and neutrons. Okay, so you know the protons have a positive charge. You know the neutrons have a neutral charge. That means that there's no charge. Okay, so the nucleus is, this is where the mass is at. Okay, where the mass is at. Okay, the electrons do not contribute to the mass. The electrons are borderline imaginary. Okay, borderline spooky. All right. So in the nucleus we have the mass. Okay, we got the protons and we got the neutrons, and each one of these both have a mass of 1 AMU, which is just atomic mass unit. Okay, we make it easy. We just say each one of those has a mass of 1. AMU is an arbitrary unit. Okay, we call it atomic mass unit and call it 1 just to make it easy. Okay, it basically just accounts for how many of them there is. All right, so that's the nucleus. Remember when Rutherford was experimenting with shooting radioactive particles through gold foil? He saw that most of the time the particles passed through unobstructed. Every once in a while they deflected and bounced off. So that told him that the atom was mostly empty space. Okay, and since the radioactive particles he was shooting at them, the alpha particles, were positive charged because they were basically protons. Since they were deflecting off of the nucleus, he stated that the nucleus was positive. Okay, I don't want to get too much into the experiments, but that's some good info on the nucleus. Okay, remember, it's where the mass is at. It's where protons and neutrons are at. Protons are positive, neutrons are neutral. Both of these have a mass of 1 atomic mass unit. Okay, so then you have the electrons. Okay, they orbit around the nucleus. They're attracted to the nucleus because the nucleus is positive. Electrons are negative. Okay, for the atom to be balanced and have no net charge, you need to have 1 electron for every proton. Okay, if you have more electrons than protons, you're going to be negative charged. If you have more protons than electrons, you're going to be positively charged. Okay, so now remember that the atomic structure, this Bohr model, which is a great model of the atomic structure because it shows us how many orbitals there are and how many electrons in each one of those orbitals. It's a reflection of where each element sits on its periodic table. Okay, which is strange. So let's talk about the periodic table again. Remember, Dmitri Mendeleev was the scientist that's credited with giving us the best breakthroughs in developing this table. There was a lot of scientists that tried to organize the elements into a table based on similarities. Okay, but he was the first one to really understand the patterns. Okay, he looked at like all the known elements at the time, which was late 1800s, and he looked at properties. Okay, chemical and physical properties. Some physical properties he looked at were like the density, okay, the melting point, the boiling point, the like the appearance, if they're shiny. He like took all these properties and he organized the elements based on similarities, and not only similarities but like gradual changes in these properties, and he organized them. Okay, he was the first one to point out that it was likely that there was more elements to be discovered, that there was gaps in the table, and he predicted properties of elements before they were discovered. Okay, that was the main breakthrough. He realized that there was going to be more elements to be discovered, and he predicted the properties of those elements based on gaps he's seen in basically pattern recognition. Okay, so this is a key point. The periodic table is organized because it shows trends in properties. All right, so what determines the properties that we observe in the real world? It's the atomic structure, okay? Because what makes each element unique is its unique atomic structure. That's what it's made of. That's the inner workings of it. That creates the properties. Okay, so not only is the organization of the periodic table a reflection of their properties, but because those properties are determined by the atomic structure, it's also a reflection of the atomic structure. Okay, so as you notice, like remember this number up top, at the top of each entry, each element, is called the atomic number, and that number starts at 1 with hydrogen. Okay, because that atomic number tells you the amount of protons. Okay, so hydrogen's 1, helium has 2 protons, and as we go left to right, top to bottom like a book, you increase by 1 proton every time. Okay, so that tells us right there, because the protons add to the mass, that tells us right there that as you move left to right, top to bottom, these elements are organized by their atomic mass, which is related to their density. Okay, because if the atoms get heavier, that means that the material is going to get more dense. So that was one of the things Dmitry Mendeleev did, was he organized these based on like increasing density. Okay, and so that was how he kind of organized, one of the ways he organized left to right. And then remember top to bottom, so if the horizontal, okay, as we move left to right, those are the rows of the periodic table. As we go straight down, remember vertical is called columns. And elements in the same column are called families, because not families, they're called groups, because they have shared behaviors. We looked at the first column. This is the alkali earth metals. Okay, these have a shared chemical property that when you drop them in water, they explode. Okay, so, and we know that all the way on the right here, these noble gases, this group, we know that they have a shared chemical property that they are unreactive. Okay, they don't react with stuff. So elements in the same column are called groups, because they're grouped because they have similar properties. Versus left to right, you have, as you move left to right, we have gradual change in properties of the elements. Now the reason why the periodic table is called the periodic table of elements is because the properties, you have recurring properties periodically. So every time we gradually change through the rows, you have gradual changes in properties, and then you come back to recurring properties. Okay, so lithium, sodium, potassium, those are the alkali metals, like this whole column. Okay, minus hydrogen. Okay, hydrogen is not an alkali metal. Okay, there's kind of like exceptions to the rule throughout the periodic table. Like like this is not perfect, but they do their best. Okay, so hydrogen is technically not an alkali metal, but it's in the first column. But like you're just gonna have to like if I explain every little detail right now, it's just gonna confuse you guys. So hydrogen, yes, it's in the first column, but it's not an alkali metal. But the alkali metals, they have recurring properties. Okay, so as you start with lithium, you gradually change across the row. You get back to sodium, and you have a recurring property. Okay, you drop it in water and it explodes. Okay, so that's similar to musical notes. Okay, you play one note. You start with, say, C, playing C major. You move through the scale. You come back to C at a higher octave. Okay, so it's the same thing. You have a change in notes, and then eventually you come back to the same note. Okay, that's kind of what we have here. As you start, every time you start a new row, okay, each element has the same properties as the element above it. Okay, that's why it's called the periodic table, because the properties periodically are observed, like repeated. Okay, so why is the properties periodically repeated? Once again, we see in like real life, we drop sodium and potassium into water, it explodes. But what is causing that property? Remember, what causes the property? The atomic structure. Okay, so let's see, what is it about the atomic structure that those elements have in common that makes them behave the same way and puts them in the same group? Okay, so now this is where we come back to looking at the Bohr model, and once again why the Bohr model is useful. So remember, the elements are organized based on similarities. Okay, they're based on trends in behavior, but that behavior is reflective of the atomic structure. So as scientists continue to learn more and do more experimentation, okay, they learn more about atomic structure, come to find out. So for example, we looked at the hydrogen and helium lamps with our spectroscopes, and we saw the spectral lines, and we talked about how those, like, light is the emission of the release of energy from atoms when they get excited. The electrons are whizzing around, they get excited to higher energy orbitals. Okay, these are the energy levels. Okay, the atom absorbs energy, the electron gets promoted to a higher energy level called an excited state. Okay, energy has to be released, it has to be dissipated. You put a pot of boiling water on the stove, that water gets hot, it boils in a steam. Like, energy wants to get away from itself, it has to be dissipated. Okay, when those electrons absorb energy and get promoted to an excited state, they have to release that energy. Okay, as they release that energy and relax back down to their normal state or ground state, the energy released is electromagnetic radiation, which is the light that we see. Okay, so when we looked through the spectroscopes and we saw the very sharp spectral lines, those were representative of the electrons relaxing from different excited states. Okay, so we know that atoms have energy levels that the electrons sit in. Okay, and we know that the way this is organized, the first row corresponds to the first energy level or orbital, the shell. Okay, so, and we know that because there's two elements in that first column before the properties repeat, we know that there's only two, and the atomic number goes up by 2, and there has to be 1 electron for each proton. We know that there's only 2 electrons in that first orbital. Okay, so that's a lot to think about right now. So just know that because there's only 2 columns occupied by elements in the first row, hydrogen and helium, those are just 2 columns that are occupied by elements. That signifies that only 2 electrons can fit in that first energy level. Okay, which is, remember, the rows represent the energy levels, which are the rings around the nucleus. Okay, so once again, there's 2 occupied columns in the first row, hydrogen and helium, which signifies 2 protons and 1 electron for each one of those protons, so 2 electrons in that energy level. Okay, when we move to the second energy level or orbital, second row, we see that there's 1, 2, 3, 4, 5, 6, 7, 8. Okay, there's 8 electrons that can fit in that second row, that second layer or second orbital energy level, whatever you want to call it. Okay, so that's why we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that second layer. Okay, when we move to the third row, once again, a total of 8 can fit. Okay, 8 can fit. But this is the Bohr model for sulfur. So sulfur right here is in the 1, 2, 3, 4, 5, 6th column. Okay, so sulfur only has 6 electrons in the outermost column. So 1, 2, 3, 4, 5, 6. If it was argon, it would have all 8 electrons in that outermost layer. Okay, when you have the when the orbital is full, okay, with 8 electrons, that's called an octet. Okay, that's desirable. They like that because they're completed. Okay, that's going to be more kind of stuff we're going to talk about next semester. But okay, so that's how you draw the Bohr model. Okay, whatever ring the element is in, or excuse me, whatever row the element is in, that's how many rings you draw. Whatever column you're in, 1, 2, 3, 4, 5, 6, whatever column you're in tells you how many electrons are going to be in that outermost ring, which is called the valence electron shell. Okay? Now remember, as these elements go down the periodic table, they're getting bigger. Okay? They're getting more protons, and that means they're gaining more electrons to orbit those protons and balance, neutralize the atom. So in order to get to this third row, sulfur is in the third row, we don't get there without filling up the previous 2 rings. Okay, so make sure that if you're in the third row, all the rings underneath it inside are filled with the maximum amount of electrons. And remember, the first row can fit 1, 2 electrons because there's 2 columns occupied in that first row. In the second row and the third row, you can fit a maximum of 8. Okay, so this semester we're only going to the third row. So you're probably going, well, Mr. Peterson, when you get to the fourth row, you have 18 columns occupied because you got all these in between here now all of a sudden become a thing. Okay, now we're not worried about that till next semester. But yes, when you get to the fourth row, the fourth layer, all of a sudden you can fit 18 electrons. Okay, this is just a sneak peek. Don't worry about this right now. But like you're starting to see a pattern here. You're seeing the first row you can only fit 2, second and third row you can fit 8, and then you can fit 18. And that makes sense because as the atom gets bigger, there's more spherical space around the atom for electrons to fit into. Okay? So don't worry about after third row. We're only doing this semester. And remember that just because these are not occupied, these columns right here in the first 3 rows in the middle, that there's no elements occupying those columns, that doesn't mean that we're waiting for more elements to be discovered. Like this thing is complete. This thing is complete right now. The reason why those are not there is because there's not enough room for electrons in those columns. All right. So I know that's a lot. As we get deeper into chemistry, like you kind of just have to accept some stuff at this point, and then like marinate on it. And then when we get into next semester, like you'll learn more, and then the pieces will start to fit together. Okay, more patterns will uncover themselves. But right now, there's some things that you're just gonna have to accept. Okay. But remember some important things. This periodic table is organized based on observed properties, okay? And then later as time went by and we learned more about atomic structure, we found out that it's the atomic structure that determines those properties, okay? And so that's pretty interesting. Okay, so I'm going to do one more thing talking about groups, because this is also important. Okay, so remember lithium, sodium, and potassium. Those are the alkali metals. They're all in the first column, and they all have similar properties. They all explode when you drop them in water. So, because the atomic structure determines the properties, there must be something similar about their atomic structure. So let's draw the Bohr model and see what's similar about their atomic structure. Okay, so lithium is in the second row. Okay, lithium, second row. Okay, so that means 2 rings. Okay, you know that the first row has 2 occupied columns, so 2 electrons can fit in that first row. Okay, we're in the we're in the first column, so that means 1 electron in the outer orbital. Okay, sodium. Sodium is in the third row, so that's 3 rings. 1, 2, 3. Okay, you know 2 electrons can fit in the first. To get to the third row, we got to fill up the first 2. To get to the third layer, you got to fill up the first 2 first. Okay, so 2 electrons. Okay, second row can fit 8. We had to get all 8 before we can start the third. Okay, and then how many electrons in the outermost? It's in the first column. Okay, so that's 1. Again. Okay, you're probably already seeing a pattern. Let's draw K just in case. And we already did this in class, so should be familiar with this, but it's a nice refresher. Okay, potassium, K is the chemical symbol for potassium, is in the 4th column. The 4th row, so that means 4 rings. Okay, 2 electrons fit in the first column, 8 in the first row or layer. 8 fit in the second layer. 8 fit in the third layer. And once again, the outermost is going to have 1 because it's in the first column. Okay, so the thing that these have in common is they all have 1 electron in the valence electron shell. Okay, so that's what's similar about the atomic structure. So that's a big hint that chemical properties are definitely have some relation to the valence electrons. Valence electrons are the amount of electrons in the outermost layer. Okay, so remember, these are a group. They got similar properties, and that's because what's similar about the atomic structure is 1 valence electron. All right, and every element that's in the same column has the same number of valence electrons as the element above it, all the elements above it. Okay, all elements in the same column have the same number of valence electrons. They got similar chemical properties, and they're called groups. The only groups we've talked about so far are the alkali metals and the noble gases. Okay. One final thing. Some of you guys are still struggling with calculating the atomic mass. Okay. Some of you guys are still struggling with calculating the atomic mass. Okay, so let's do, this periodic table is not great because it doesn't have the atomic mass written down, but let's do chlorine. Okay. Chlorine has an atomic number of 17. Okay, that means you got 17 protons. Okay. And it's got an atomic mass of 35.453. Okay, so this is a big area of confusion. If this atomic mass tells you how many protons and neutrons there are, then and neutrons, and both of those have an atomic mass of 1 AMU, how do you get 35.453? How can there be a decimal if it has to be whole numbers? And the answer to that is you always have 17 protons, but this is an average mass. So that means that you can have varying number of neutrons. And like I said, neutrons are mysterious, okay? Like, we don't really fully understand what purpose they serve in the atomic structure. Okay, we know that they affect the stability, okay, but they don't affect the charge, and we don't know a whole lot about them, okay? And we're not going to learn much about them in this class because that's kind of beyond the scope of this class. You learn about that later in college chemistry. So, this is an average, but we know we can calculate approximately how many neutrons there are by this is protons and neutrons, and this is number of protons. You can subtract this from that and find out approximately how many neutrons there are. So let's do it. 35.453 minus 17 is going to be 15 minus 7 equals 8. 2 minus 1 equals 1. Okay, so 18.453. Okay, so there's approximately 18.453 neutrons. Okay, so that means that some of the time it could have 18, okay, or some of the time it could have 19, okay. But because this is closest to 18, okay, it's 18.4. So we would usually, because this is less than a half, we would usually round that down to 18. We say that it's probably closer, it's probably more likely to be 18, but sometimes in nature you would find it with 19, okay? So this is, once again, this is an average. Okay, it means that you got varying level of neutrons. I always ask you, what is the approximate number of neutrons? Okay, and the answer is going to be 18, 19 is fine. You could write 18.453. You could round that to 18.5. Right, it's an approximate, so it don't really matter. Okay, so that's, if you got any questions on this, email me, okay? Come to me in class, lunch, whenever, all right? If you have trouble with this video, slow it down, okay? Slow down the playback speed, and remember, you can find this information everywhere. It's your responsibility to learn this stuff. Like, I am the teacher, but at the end of the day, like, you gotta figure it out. Okay, so you need to, if you're not learning from this, you need to type up the subject that you're having trouble with in YouTube, Google. There's YouTube videos are a dime a dozen on this stuff. Okay, you got a textbook you can look at. You can look in the index on the subject. Okay, so you guys should all do great on this final. All right. Okay, hope that helps.